When forces act on an object, we know that they can alter its motion. However, they can also alter its shape. This video connects forces and elasticity together. I'll go over understanding the main ways an object can deform, relating the force applied to the extension or compression of an object, and finally applying our knowledge of energy to elasticity. We know that you can change the shape of an object by stretching it, squeezing it, compressing it, squashing it, and whatnot. Now here are two objects. One has two forces applied to stretch it, and when the forces are removed, it returns back to its original shape. The other is squashed by a force, but when that force goes away, it stays squashed. We can group deformations into two categories: elastic deformations and inelastic deformations. Elastic deformations are those where, when the forces deforming the object are removed, the object returns to its original shape. On the other hand, inelastic deformations are those where the object is permanently deformed. Even when the forces are removed, it will keep its deformed shape. And from this info, we get the definition of an elastic object. It reads suspiciously like what an elastic deformation is. It's an object which will return to its original shape when the forces deforming it are removed. By understanding deformation, we can now explore the link between forces and elasticity. First, we'll look at forces and extension. Let's say I have a coil spring like this. Its length would be this big, and when I hang a mass on it, unsurprisingly, it extends and its length increases. If I increase that mass, it extends some more. The extension of the spring is actually directly proportional to the force applied, and vice versa. We summarize that with this equation. Force is equal to the spring constant multiplied by extension. The spring constant is a property intrinsic to a spring. It tells us how stiff the spring is. The higher the spring constant, the more force you'll need to get the same extension. In symbol notation, the equation summarizes to F equals Ke. The units for force are newtons, the units for extension are meters, and that tells us the units of the spring constant must be newtons per meter. To determine the extension, we first need to know the original length of the spring, shown in pink, then subtract that from the new length of the spring, shown in yellow. And as I said before, the higher the spring constant, the stiffer the spring. There's another major factor that affects springs, and that's their limit of proportionality. I've got that coil spring here again. I'm going to plot a graph of its extension against the force being applied to the spring. Initially, as expected, the force and extension are directly proportional. We have a straight line that goes through the origin. But then, it reaches a point beyond which suddenly, the spring extends more than expected, with only a small increase in the force. This point is known as the limit of proportionality. The extension of a spring is directly proportional to the force applied, as long as it does not go beyond its limit of proportionality. This is called Hooke's law, which is summarized by the equation I showed you earlier. It's also important to note that the area underneath the graph is equal to the elastic energy stored in the object, which, thinking back to the energy transfers topic, we know is also equal to a half of the spring constant multiplied by the extension of the object squared. You can also calculate the spring constant of the object by calculating the gradient of the directly proportional section of the line. Hopefully that gave you a quick overview of forces and how they are related to elasticity. You should now be able to use this information to carry out a practical to investigate the extension of a spring. A study tip I'll leave you with is that Hooke's law can also be applied to compressions. The extension in the equation will just be in the opposite direction. After all, force is a vector.